13, Introduction to Light. Purpose. I will learn how previous concepts of sound waves relate to light waves. I will learn how light is made. Relevance. The study of light is a basic concept of physics, just like learning forces last semester. Phones away at this time, phones away. Forces is a basic idea. Velocity, basic idea. Electricity, basic idea. So light is basic as well. Success. You'll be able to see what light is, how it's made, and how to measure it. We have a homework assignment tonight and a quiz next week. The ability to fool our eyes is more well known. We have all seen optical illusions. Below is a picture where it looks like the squares are either one dark shade or one light shade, either black or white. Actually, it's a lot more complicated. Our brain recognizes this as a checkerboard of two colors with a shadow running across it. The brain says, I have seen the situation very often with shadows on gray and white patterns. And so it convinces our inner self what the brain expects to be the real case. It expects there to be black squares and white squares. But actually, squares A and B, they look like that's a black square. It looks like that's a white square. They're actually the same color. You might think to yourself, no, I can clearly see that A is darker. That's no doubt. Well, let's cover up everything else besides A and B.
So different. So different. Holy crap. I see it.
Such a bad way of demonstrating this.
There. A and B are exactly the same shade. Okay, time to refocus, please. Time to refocus, please. If we cover up everything else, we can see that A and B are exactly the same shade. But when we put it into the context of a checkerboard, our brain thinks it knows what's going on and changes our perception of it. So this is why, even in a court of law, you have to be careful about what does a witness say they saw. They can be absolutely sure, I saw a red car. But when you look at closer examination, it's actually a different car. How could that be? Well, if you are at night and you are under these sodium vapor street lights, they give off a bluish color. And so you might have a car that's orange, but under this light it looks red, or something along that lines. But it even gets more complicated than that. Have you ever seen the TV show Brain Games? I highly recommend it. You can see it on YouTube all over the place. And they will give you lots of examples of how our brain can be mistaken about stuff. Okay, we need 20 minutes, and we've got 20 minutes. Excellent. The name of the study of light is called optics. So, optical glasses. An optician gives you glasses. An ophthalmologist helps diseases of the eye. Optics referring to light. It is made out of electric and magnetic fields. There are no particles that hit your eyeball to create the vision. It is electric fields, magnetic fields, and they both happen at the same time. You can't separate one completely from the other. They're always going to be hooked together. In the diagram below, these are labeled as E and B. Here's the B, and here is the E. So the E is the up and down, and in the Y-axis. Now this B is shown as an angle, but what that's trying to represent is coming straight up out of the paper, like my pen is at this moment. Trying to represent that. How do they change? They grow, and then they shrink, and then they flip, and then they repeats. Grows, shrinks, flips, repeats. So the electric field is getting bigger and bigger and bigger and bigger, and then it shrinks smaller and smaller and smaller and smaller. Then it flips bigger, 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 smaller, 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 and then it's going to flip. It's going to keep on going. The two components always are at 90 degrees to each other. So they're called perpendicular vectors. Remember in geometry class, the symbol for right angles, perpendicular, it's a little square. So go ahead and put those in these little nooks and crannies here, the corners, the vertex. Because of these two components, the electric and the magnetic fields, we call light oftentimes electromagnetic radiation. Radiation meaning it's going out in all directions. It radiates outwards. So this radiation is usually very, very harmless, benign, safe. Not all radiation is bad. We usually use the word radiation in terms of like nuclear power plants or nuclear bombs, and yes, that radiation is bad. But this kind of radiation is just fine and dandy. In normal light, electric fields of different light beams are arranged randomly. In other words, in some light beams the E is up and down, in other places the E is sideways, and in others it's at an angle. It's all randomized. When all beams have their electric fields orientated in the same axis, it's called polarized light. Polarized light. If the electric fields are lined up, the magnetic fields are automatically lined up as well, because they're always at 90 degrees. So to polarize light, you send it through some filters where there are simple little slots that only allow electric fields to go through in one orientation. If they are angled in a different way, they cannot get through the slots, and so they get blocked. Imagine the filter like a piece of wood with a little slot cut through it, like this picture here. And the electric beams, electric fields, are like sticks that you're trying to throw through in this orientation to get through the slot. Here I have a box, a game. I'll let you guys play this later on after the notes. So I have the slot here, and the stick represents the electric field, the slot represents the filter, and you have to get it through here, and that works. That way the stick can go through. If you have the electric field orientated in another way, it's going to get blocked and just bounce backwards. That's how your sunglasses work and other polarizing filters. But I have candy for anybody who can successfully do that from 4 feet away. It's harder than you think. Number 8, we perceive light of different amplitudes as brightnesses. Bigger amplitude means brighter light. Just like a bigger amplitude of sound waves means a louder sound, a loud light beam would be like brightness. Okay, other types of electromagnetic radiation. We perceive light of different wavelengths or frequencies as different colors. Infrared is going to have, let's see here, red down here at this end, 700 nanometers in wavelength, and violet down here at 400. Yellow is going to be in the middle, about 550 nanometers of length from one crest to the next. When I say different wavelengths or different frequencies, both of those, changing one will change the color. Because when you change a wavelength, you're automatically changing the frequency as well. Number 10. What has a frequency of 9 gigahertz? Well, let's see here. 10 to the third, that's 1,000. That's going to be the prefix kilo. 10 to the sixth, that's 1,000,000. And the prefix for that is mega. 10 to the ninth, that's 1,000,000,000. That is the prefix giga. So that's going to be a frequency of 9 gigahertz is 9 times 10 to the ninth hertz. So looking up here, let's see here, this is wavelength on the bottom, frequency on the top, 10 to the ninth. That's going to be right around in here. That's going to be the microwaves. Just like in your ovens at home in the kitchen. Microwave oven produces this light. We cannot see that light. Our eyes are not sensitive to that frequency. But the food, particularly the water molecules in the food, absorb that energy and turn it into thermal. Frequency of 5 megahertz. Mega is million, that's times 10 to the sixth. So 5 times 10 to the 6th is what? 10 to the 6th, that's AM radio. So the only difference between the microwaves that heat up your food and the radio waves that make music in your car is the frequency and wavelength. It's the same stuff, the same electric and magnetic fields. They're just interacting in different ways. Yes?
This is kind of topic, but how do we tap into those waves and speak to them? How do we make noises?
The AM radio waves, the magnetic fields and electric fields, push and pull on the electrons in your antenna. And then so that creates a little current in the antenna with electrons going up and down. And the circuitry of the radio amplifies that and uses it to make a speaker go back and forth, and that makes the sound waves. The frequency of 3 kilohertz. Kilo is 1,000 times 10 to the third. So 3 times 10 to the third. What's that going to be? 10 to the third is up here, long radio waves. You've heard of shortwave radio? That kind of a thing. There's also long wave radio. I believe only the military uses that. I'm not sure. What are nanometers? Nanometers are millionths. Millionths, that's going to be times 10 to the negative 6. Now this is nanometers. That's a length. Meters, a distance between crests. So that's wavelength. 10 to the negative 6, that's infrared. So the infrared lights, the heat lamps that are above the fry station at McDonald's, those are producing infrared radiation, has millionths of a meter between crests. Compare visible light to the other parts of the electromagnetic spectrum. Comparisons: visible light and everything else here, X-rays, UV rays, microwaves, gamma rays, etc., all of those have the same electric and magnetic fields. The stuff, so to speak, the components that make up the beams are exactly the same. Electric fields, magnetic fields, perpendicular, growing, shrinking, flipping, growing, shrinking, flipping. Contrasts, different sizes, different wavelengths, different frequencies. The boundaries between these spectrums are fuzzy. Non-distinct? I think that's a word. There's not a firm line where if you're a smidgen bigger, you're an infrared ray. If you're a smidgen smaller, you are a red visible light ray. It's kind of blurry. There's not one place where it's either AM or it's FM radio. There's a place where it can be both. There is evidence that, using the spectrum, there's evidence that bees can see into the ultraviolet spectrum that we can't see. We can see blue, and then we can see purple, and then it disappears, and we don't see it. Those things can hit our eyes, and it doesn't stimulate our nerves at all. But bees, apparently, they can be stimulated by these things in ultraviolet. We can see a picture here. This is in normal light. It's just a yellow flower. But in ultraviolet, it has this target in the center. A dark, it's almost black in the center with ultraviolet. And so they think that maybe that attracts the bees to go down to the middle where the pollen is. Maybe. We've been asking the Bee Association, and they won't respond to our calls, so we don't know for sure, but it's a good guess. Military uses infrared in their night vision goggles. So they will have a flashlight with a special... No, I take it back. There's a couple different ways of doing night vision. One of them is the infrared, where they have these goggles that are sensitive to it. And our bodies, just because they're warm, give off infrared. The hotter it is, the more infrared is given off. And so these things will see that. And things that are really hot will be colored red in the computer. And things that are cooler will be interpreted and colored blue. And so we see those visible lights in response to the heat lights, so to speak. Parts of our body can detect infrared. Okay, our eyeballs detect visible light. What part of our body detects infrared? I was just saying here that different temperatures. Hot gives off more infrared. What part of our body can detect heat?
Brain.
If I was standing next to a campfire, I could close my eyes, I could tell you which way the campfire is, right? Just by feeling, like, wow, this is really hot over here, the campfire must be over there somewhere. My skin detected the infrared. Let's stop our talking, please. Okay, so that's how we use the spectrum. Back here is how we have the different parts of the spectrum. Back here is what everything is made out of in that spectrum, electromagnetic field. Okay, now how is this spectrum made? How do we get these pieces of light, these beams of light shining? Visible light waves can be made when electrons go to smaller orbits. Orbits that are far away from the nucleus have high energy. Orbits that are close to the nucleus have low energy. And so when you go from a high energy, high orbit to a low energy, low orbit, you got to give off some of that extra energy. And that's given off as light waves. Gamma rays are made when the protons shift inwards. If I take a nice round nucleus here, and there are instances where a piece of it is going to fall out. And so there's a hole, so to speak, that develops, a divot, a ditch. So then the outside protons shift down into that hole and make a slightly smaller nucleus. Protons are falling inwards as they shift. And that's when the gamma rays are given off. Radio waves can be made when electrons are accelerated. In the antenna. The transmitting antennas of walkie-talkies, of a giant radio tower, or the little hidden ones in your cell phone. Your cell phone, remember, works as basically a radio. So in the antenna, electrons are being accelerated up and down, faster, slower, more, less. And when they do that, they release radio waves. Microwaves and X-rays are made when electrons are made to jump between certain metals. Tungsten is a metal that is used for X-ray machines, I understand. You shoot high energy electrons at a tungsten metal, and it gives off X-rays. And then your dentist uses them, your doctor uses them to shoot through your body. Okay, so that's the end of the notes. You have this reading about being an X-ray technician. That's a very good career if you're interested in medical stuff, but you don't want to go through years and years and years and years and years and years and years of training. You can get a 2-year degree and become an X-ray technician. And then we have, that's the end. I hope there's questions, homework 113 in Schoology.